Hi everyone, welcome to the Chem Help ASAP Wednesday live stream. I hope that you are all doing well. This week we are going to be talking about acids and bases, and we're going to be talking about them in aqueous solutions. Now we will deal with not only strong acids and bases, but also weak acids and bases. Now, for this particular week, we are going to deal with them separately. So we're just going to be talking about solutions of, like, say, a weak acid or a solution of a strong base. But for next week, we are going to talk about when acids and bases react. So if you want to have more information about reactions of acids and bases, then that is definitely on my plan for next week. But before we can do acids and bases reacting with each other, we need to make sure that we can deal with them just on their own. So that is what we're going to do today. We're going to do a lot of different kinds of problems. So I want to make sure I kind of mix it up a little bit, and it's not always here's a concentration, what is the pH? Here's a concentration, what is the pH? We'll do a little bit of that, but I also like to make sure we work backwards and we deal with things like equilibrium and throw in other interesting twists like density and percent dissociation and all of that good stuff. So I will warn you, I don't think my microphone is going to pick it up, but we are having some thunderstorms right now. So if you hear a little bit of thunder, that is going to be on my end. So just wanted to give you a heads up on that. Okay. With that intro being said, let's go ahead and get started with our first problem with acids and bases. All right. Okay, so again, just like I try to always do, I try to always start with a simple and an easier problem. So this question is, what is the pH of a 125 milliliter solution that contains 93.2 grams of sodium hydroxide? So this is your very, very classic. We've got a strong base in solution, and we just want to know the pH of that solution. So let's go ahead and start. Oops, I like using that one. Start work on this one. Okay. So I think the best place to start with this is to remember how we calculate pH. So pH is the negative log of your concentration of hydronium. Now, just as an aside, I'll do this in green. You might also see this formula where instead of hydronium, you just have concentration of protons or concentration of H+. These are equivalent. It is the exact same thing. It's just when we're in aqueous solutions, all of your H+ attaches itself to a water molecule. So in reality, you're really measuring hydronium. But in terms of the math and how you set up the problem, you use whichever form is easiest and makes the most sense to you. I always tend to use the hydronium form, but again, just so you know, you can always change that to H+. Okay, as that aside has been said, here is our formula for calculating pH. So we only really need one thing to calculate pH, and we need the concentration of hydronium ion. Okay, well, I immediately think concentration, specifically that concentration is molarity. So if you remember, molarity is moles of solute over liters of solution. And so what this triggers for me in terms of the problem is I have my volume of solution. Okay, so like I know I can already plug in for the denominator like pretty much straight away. I just have to convert that milliliters to liters. In moles, I've got 93.2 grams of sodium hydroxide. That's just a simple conversion from grams to moles using the molar mass. So I'm feeling pretty comfortable that I can go ahead and get a concentration right off the bat. So let's go ahead and do that. So the most work is going to be to take this grams of sodium hydroxide and convert it into moles. So if we have 93.2 grams of sodium hydroxide, we are going to use the molar mass to convert that into moles. So the molar mass for sodium hydroxide is 39.997 grams per mole, and that gives us 2.33 moles of sodium hydroxide. Okay, so we have our moles and we can get our concentration. So if I'm going to plug into molarity, I have my moles, my 2.33 moles of sodium hydroxide. And that is over my liters of solution. So I'm just going to take my 125 milliliters. Of course, it's a simple divide by 1,000, and that will give you your liters. So that's 0.125 liters of solution. And this will give me my concentration. And that is 18.6. Again, that is molarity. And that, whoa, sorry. That N got a little out of control. Sodium hydroxide. All right, so I'm a little bit closer, but I'm not quite there yet, right? Because for pH, I need my concentration of hydronium. Right now I have concentration of sodium hydroxide. So how am I going to connect these two? Well, there are a couple of different ways to connect it. The way I think of it is I know that I can also calculate pOH, and that is simply the negative log of my hydroxide concentration. And I can get hydroxide concentration from my sodium hydroxide. So sodium hydroxide is a strong base. When you put it in aqueous solution, you get sodium cations and hydroxide anions. Now, the great thing about sodium hydroxide is your mole ratio from sodium hydroxide to hydroxide is 1:1. So that means this 18.6 molarity for my sodium hydroxide is the concentration of my hydroxide. It is the same thing. So I am going to say 18.6, this is molarity of hydroxide anion. So we will deal with another problem where we don't have this 1:1 ratio, but the 1:1 ratio just means that you have to recognize that it is a 1:1 ratio and you don't need any extra math, but it's great because my concentration of sodium hydroxide is my concentration of hydroxide, which means I can plug this concentration of hydroxide into my formula for pOH and calculate my pOH. Okay, so I'm just going to do the negative log of 18.6, and that is molarity. And let's see, I did do this calculation, and I get negative 1.27. All right, so a negative, that's actually completely fine. You can get a negative pH, you can get a negative pOH, so don't panic about that. This is a strong base and it's a very concentrated base. So having a negative pOH is not a problem. Now, the question though didn't ask for pOH, it asked for pH. So we need to connect pOH and pH, and that formula is pH plus pOH equals 14. So it's a really, really simple formula. So that means all I need to do is plug in my value for pOH. And yes, make sure you keep the negative here. And so that is going to give me a pH of 15.27. Now, that should make logical sense to you if you're comfortable with the pH scale. This is a base. Bases have pHs that are greater than 7. So this definitely has a pH that's greater than 7. It's also a strong base that is also very concentrated. So having a number that's greater than 14 is also a good sign. That is something we would expect from a concentrated and a strong base. So that is the answer to our first question. Let's make sure that there aren't any questions in the chat. Nope. Okay, great. Let's move on. Okay, so now we're going to go to some acids. A 100 milliliter solution of hydrochloric acid has a pH of 2. How many milliliters of water should be added to the solution to raise the pH to 4? Okay, so I don't know if y'all heard that, but there's just a little bit of thunder that came in through there, so it sounds like the storms are still coming through. Okay, so back to my acid problem. So what we've got here is not just a straight up, this is an acid in solution, but we've got to do a dilution problem here as well. So this is what I mean about trying to bring other concepts into the acids and bases so that you can start to synthesize all of these different chemistry concepts together. All right. So what I'm seeing here is I have a pH of 2, and I also know the volume of that solution. What I don't know is the volume of my pH of 4 yet. So let's start with calculating how many moles of hydrochloric acid I have in this 100 milliliter solution that has a pH of 2. Again, remembering that pH is equal to negative log of my hydronium concentration. All right, but I also need to connect my hydronium concentration to my hydrochloric acid, just like we did for our sodium hydroxide in the previous problem. The great thing is this is another one-to-one. So hydrochloric acid in water gives the hydronium ion and a chloride anion. All right, and you can see from this chemical equation, everything is a one-to-one ratio, which means my concentration of hydrochloric acid is my concentration of hydronium ion and vice versa. So figuring out the concentration of my hydrochloric acid will give me my concentration of hydronium ion. So I have, for my pH of 2, let me switch back to blue. For my pH of 2, I can calculate what my concentration is. So if I do that math, I get a concentration of hydronium of times 10 to the negative second, and that is molarity. All right, my concentration is definitely going to change as I dilute this. But what is not going to change is my number of moles of hydronium ion, or you could even think of it as number of moles of hydrochloric acid in solution. Both are going to give you the same answer. So because I know that I have 100 milliliters of this solution, I can calculate how many moles of hydronium I have. So remember, molarity equals moles of solute over liters of solution. So in this case, my solute is my hydronium ion. Okay, my concentration, I know, times 10 to the negative second. I'm going to calculate my moles of hydronium. Again, that is going to stay consistent through the dilutions. That is not going to change. And my liters of solution, I have 100 milliliters, so that is 0.1000 liters. So I can calculate my moles of hydronium. And when you do this calculation, you get 0 times 10 to the negative third moles of hydronium. Okay, so now that I have the moles of hydronium, I can then use my moles, which are consistent, and my pH to figure out what my volume of solution is going to be when my pH is 4. Okay, so now this is where like being organized helps. So now I'm going to go to my pH of 4 solution. And of course, this is also negative log of hydronium concentration, which means my hydronium concentration for my pH of 4 solution is 1.0 times 10 to the negative fourth. Okay, I know my number of moles in this solution. I know my concentration. I can calculate my liters of solution. Again, I'm going back to this equation here, but now I've got a new solution. Okay, so I have my concentration again here for my pH of 4. I know my moles of hydronium. This is moles of hydronium. And now I'm going to calculate my liters of solution for this particular solution of a pH of 4. And what I get is once you have a pH of 4 solution and you have this many moles, you need a solution that has 10 liters of water. Actually, let's give this, right now that only has one sig fig, let's give it another sig fig. 10 liters of solution. Okay, so I just want to point this out. This is tremendous. We have gone from 100 milliliters of solution to 10 liters of solution. So how many milliliters of water did we add? Again, we started with 100 milliliters of solution and we ended at 10 liters of solution. So that means we needed to add 9,900 milliliters of water to raise this solution from a pH of 2 to a pH of 4. That is a lot of volume. Now, why does it take so much volume to bring the pH up like this? Well, that is because hydrochloric acid is a strong acid. So that means it completely dissociates, which means you have to really dilute hydrochloric acid down quite a bit to get the pH to come up there. So remember, my number of moles of hydronium, or my number of moles of hydrochloric acid, because they're the same here, stayed the same from my pH of 2 to my pH of 4. All I changed was the amount of water in solution, or my total volume of solution. So it takes a lot of water to dilute hydrochloric acid down because it is a strong acid. Okay, all right, good. We have no questions, which means hopefully that you guys are still with me. And let's go on to our next question. All right, so we're back to bases here. A 575 milliliter solution of barium hydroxide has a pH of 10.5. How many grams of barium hydroxide are present in the solution? Okay, so this is one where we're working backwards. We have the pH and we want to figure out how many grams of barium hydroxide were added. So this is a situation, and you might have this situation in a lab where they say, okay, we need to make a solution that has this pH, and here is the base we're going to use. How much do we need to add? So this is a very, very common situation. Okay, so remembering our formula for pH, negative log of hydronium. All right, we have our pH, which means we can figure out our concentration of hydronium. But in this case, because I'm dealing with a base, I think it's actually going to be easier to first convert this pH to POH. Now, you can do this either way. You can also use your formula that connects hydronium to hydroxide concentration. So there are a lot of different ways to work the math here. That is 10 to the negative 14th there. Again, this is where if you and a friend are working the same problem side by side, you might work slightly different paths, but both get to the same answer. So just make sure you're using a method that, again, makes sense to you and that you can logically work through. All right, so I am going to first convert this pH into POH. So remember, let's maybe put it over here, pH plus POH equals 14. Of course, this equation is just the log of that equation. So if I have a pH of 10.5, I can calculate what my POH is, and that is 3.5. So now what I can use is this formula. And now I'm working with hydroxide concentration, which is what barium hydroxide is going to give me. It is a base. It is an Arrhenius base. It gives hydroxide in solution. So I just find it easier to go ahead and switch to POH and work from that. All right, so plugging in now my POH to calculate my concentration of hydroxide. And oops, I was getting ready to write hydronium. So my concentration of hydroxide is 3.16 times 10 to the negative fourth, and that is molarity. Okay, great. So now that I know the concentration of hydroxide that I want, what I am next going to do is I'm going to figure out, all right, so if that is my concentration, how many moles of barium hydroxide do I need to get that concentration? So remembering again, molarity is moles of solute, which in this case is moles of hydroxide over liters of solution. I know my concentration, I just calculated it. 3.16 times 10 to the negative fourth. I'm calculating my moles of hydroxide, so that is my variable. And for my liters of solution, that came from the problem, my 575 milliliters. Again, just a quick conversion to convert that into liters. So now I know my moles of hydroxide. Let's see, I did that calculation and I get 1.82 times 10 to the negative fourth moles, again, of hydroxide. Okay, so now that I know moles of hydroxide, I'm starting to work back to my grams of barium hydroxide. But in this case, I need to be careful about the identity of my base. So let's, I'm going to put this up here. Remember, barium hydroxide, it is a strong base. It is soluble in aqueous solution, is going to give barium cations and 2 hydroxide anions. So there is some extra stoichiometry to do. This isn't the case like sodium hydroxide or hydrochloric acid where everything is 1-to-1 and you can just say, oh, I've calculated my hydroxide concentration or my number of moles of hydroxide and it is my moles of base. Nope, this is not the case for barium hydroxide because we have a 1-to-2 or a 2-to-1 stoichiometric ratio. So we want to make sure that we use that ratio as we're converting from moles of hydroxide back to grams of barium hydroxide. So at this point, this is really just a pure stoichiometry question. So I am going to just do all of my stoichiometry in one go. So starting with my moles of hydroxide, I'm just going to rewrite this. That is an 8 times 10 to the negative fourth moles of hydroxide. I'm going to convert back to moles of barium hydroxide using my balanced chemical equation. So for every 2 moles of hydroxide, I need 1 mole of barium hydroxide. And then because my problem asked me for grams, I'm going to put 1 more conversion factor in here. And I'm just going to convert from moles of barium hydroxide to grams of barium hydroxide. Let's see, what is that? 171.34. That is grams of barium hydroxide. So I just want to point out here, I guess I'll do it in the laser pointer. See how my moles of hydroxide cancel, then my moles of barium hydroxide cancel, and I'm left with my grams of barium hydroxide, which is what the problem asked for. So again, this is just pure stoichiometry. The thing here to remember is that you're setting yourself up so that the units you want to cancel are actually canceling. Again, one of the most common mistakes I see students make when they do, especially stoichiometry, is they don't write down around their units and they end up flip-flopping their stoichiometric ratio, which is so frustrating to put all that work into a stoichiometry problem and have it wrong because you've accidentally flip-flopped something. Okay, so if I do this calculation and plug this into my calculator, I get 0.0156 grams of barium hydroxide. And that is the answer to our problem. So this one is kind of cool in the sense that we worked backwards from pH, and we had to remember we're dealing with a base, and we went to pOH, and then we brought in concentration, and then we had to bring in stoichiometry too. So this is where really you can synthesize all of these different chemistry concepts and bring it together in one problem. And really the math is not that difficult, but what I think is most difficult is knowing what formulas to pull and how to apply different concepts. Okay, it doesn't look like there are any questions in the chat, so we're going to keep on moving to my next problem. Okay, so propanoic acid has the molecular formula HC3H5O2. What is the pH of a 0.1 molar solution of propanoic acid? What is the concentration of the other species in solution? And what is the percent dissociation of propanoic acid? Okay, so what we've got here is we have a weak acid. And the thing that they did forget to give us, but this is something that you can look up, is they didn't give us the Ka of propanoic acid. So a lot of times in these cases, if you are working this problem and you're working in a textbook, then very often at the very end of the textbook, there should be a table of common weak acids and their Kas. Of course, if you're online, then Google is great for finding Kas of all different kinds of acids. So I am going to go ahead and write down the Ka. I'll put this in maybe yellow for this acid just so that we've got it ready to go. So the Ka is 1.3 times 10 to the negative fifth. Now remember, once you have a Ka, you have a weak acid, or vice versa. If you have a weak acid, you should have a Ka. I think it's easiest to differentiate between strong acids and weak acids. There aren't that many strong acids, and I find it easiest just to memorize what the common strong acids are. Now, if you're ever in a situation where you really don't know and like you're not given a Ka, then looking it up will let you know. If you have a strong acid, it does not have a Ka. So if you try to look up a Ka, say for hydrochloric acid, I think the best you're going to find is it'll just say large on it, which means it completely dissociates and there's no number to really put on it. So if you're ever in a bind and you're really not sure, you can attempt to look up a Ka, and if there is no Ka or it just says large, then it means it's a strong acid. All right, but let's go back to propanoic acid here. So we have a Ka, we have this acid in solution. So I think because we're doing a weak acid, we're going to start with our rice table or ice table, depending on how you think of it. So this is going to bring in equilibrium into this problem because, again, we're dealing with a weak acid. So let's get our balanced chemical equation. So propanoic acid. And you might see this acid written different ways. You don't have to write it this way. I'm sure the authors chose to write it like this just because they put the acidic proton first, so you know which proton is going to dissociate when you put this in aqueous solution. Okay, so this is going to give us our hydronium ion, and then it's going to give us our conjugate base. And you can see I just dissociated this first proton right here again, which is why it is written in this manner. All right, so do we know what either our number of moles of propanoic acid or our concentration is? And going back to the problem, we know our concentration. So in terms of your ice table, you can use either number of moles or concentration. Both of them are going to give you the same answer. So we know initially we have 0.1 1 molar propanoic acid, and we don't have anything on the product side. Now, for our Kas, we do ignore our column for water. We don't need to take it into account because we have been given a Ka, and that takes into account our concentration of water already. So underneath water, I'm just leaving everything blank. You don't even have to mess with it. Okay, so in terms of equilibrium here, this is definitely going to shift to the right because we have no products. So we are going to use up some amount of propanoic acid, and we are going to form some amount of both hydronium and our conjugate base. Now let's add up our columns. This is 0.1 minus x, this is x, and this is x. Okay, so now we need to write, we have our Ka, let's actually write our expression. So remember, for all equilibrium constants, it's going to be products over reactants. So in this case, we are going to have hydronium, our conjugate base, O2, and that is going to be over our original propanoic acid, C3H5O2. Again, you notice I leave water out because that value is already folded into my Ka. So even though I don't have straight up numbers for this, I can still plug in these equilibrium concentrations, and I can also plug in my value for Ka. So let's plug in everything we know. So this is 1.3 times 10 to the negative fifth. Hydronium is x, conjugate base is x, and of course this is a quantity minus x. That is in the denominator. So let's simplify this a little bit. So this is really just x squared over 0.1 minus x. This is obviously a quadratic. Now we can simplify this and use the quadratic formula, or we can test and see if maybe we can drop this minus x, because then that just makes this equation so much simpler to solve. So let's see if we can drop that minus x. So I'm going to start with what I call the 500 test. So if you take your original concentration of acid, in this case it's propanoic acid, and you put it over your Ka, that value should be greater than 5, or I should say, if it's greater than 500, then you can drop that minus x term, and you will still get the correct answer. So in this case, we have 0.1 over our Ka, which is 1.3 times 10 to the negative fifth. And that gives us 7.7 times 10 to the third. So yes, that is definitely greater than 500, which means I can drop this minus x, which is always so nice, which means my equation to solve here is simply 1.3 times 10 to the negative fifth equals x squared over 0.100. This is just so much easier to solve because all I need to do is isolate x squared and then take the square root. Okay, so solving for x, in this case, I get an x of 0.0011. All right, great, that's x. So what do we do with x, right? So we always want to make sure that we're connecting our value with x with what is physically going on in this problem. So remember, back in your ICE table, your x here is your concentration of hydronium and your concentration of conjugate base, which is part of the problem that we wanted to do. We want to know what is the concentration of all the other species. So now we know our concentration of hydronium and our concentration of conjugate base. So we have partially solved already what the question asks for. We're not quite done yet, but we've made good progress. All right, so that's fantastic. So what we also need is we need the concentration of all the species in solution. So we need our concentration of propanoic acid, but this is pretty easy. All we need to do is subtract x here. So our concentration of propanoic acid is going to be 0.1 minus our value for x, which we have right here, is 0.0011. And you can see the concentration really doesn't change all that much because this is a weak acid. And so it doesn't move, this equation doesn't move very strongly to the right, it mostly stays on the left. Okay, so if I subtract this, I get 0.0989. That is molarity. Okay, so now I have the concentration of all the species in solution. Of course, first part is what is the pH, so we can totally do that. Remember that pH is just negative log of our concentration of hydronium ion, which in this case is our value for x. Remember, your value for x is we started with concentration, so our x's are also in concentration. So this is also just really easy to do. I'm just going to plug my value for x in here, 0.0011. When I do these problems, I have to be careful that I don't drop a 0 here. I do that way too often. Okay, so our pH here is 2.96. which makes sense because we have an acid in solution, so our pH should be less than 7, and we have a weak acid, so it shouldn't be like negative 2.96. That might raise a few red flags. And the last thing we need to do is we need to do the percent dissociation, and that is very easy. I think I will switch colors because I'm getting a little bit squished here. Okay, so my percent dissociation is simply my amount that is dissociated over my initial amount. And of course, that is times 100%. Okay, so for this problem, my amount dissociated, again, is my x. I already have that. That is how much dissociated. So I'm just going to plug that in. And my initial amount is my initial amount of acid specifically. So this is my initial concentration of propanoic acid, which is 0.1000. And of course, I just multiply this by 100%. And then I get a percent dissociation of 1.1%. So really we did the work in this problem is setting up your ICE table and solving for x. That is really the hardcore math part. And then it's just taking that value of x and remembering that you've already solved for a concentration of 2 of your 3 species. That's great. And you can use the x to solve for your third. And again, the percent dissociation is really, really easy again because you already have your x. You've already done that work. It's just making sure that you've answered all the parts of the question as well. Okay, so we do have a question. Could you explain again why we're able to drop the x? Yes. Okay, so this is the 500 rule. It's a way that we can know if this approximation is going to work or not. Oh, there is actually another test that we can do. Well, it's actually the percent dissociation test. But that's an excellent question. So there are really 2 different tests that we can do to see if we can make this assumption. And what we assume is that x is so small, it's really not changing, in this case, that 0.1. And you can see when we calculated the concentration of our propanoic acid, like it's 0.1 minus 0.0011. And the other test you can do is called the 5% rule, and it's really just calculating the percent dissociation, but I'll put it up here. So the 5% rule is, now you have to do the 5% rule after you've calculated x, so just FYI on that. If you take your value of x that you calculated and you put it over your initial concentration of your acid times 100%, if that is less than 5%, then that means your assumption is okay, it's fine to assume that, and it doesn't introduce enough error into your calculation to actually make a significant impact. So you can see that this 5% rule calculation is actually the same as this amount dissociated. So I put my value for x, which I did right here, up here, And then, of course, my initial concentration of acid is a 0.11. So you can see we've actually done this calculation and we get 1.1%, which is less than 5%. Now, the other thing I will say is you can go back to this original equation right here, or maybe I'd say this one right here, and you can use the quadratic equation to actually solve for x, and then there is no error in that value of x. Now, I have not actually done that calculation, so I cannot tell you what it is. I checked my approximation, so I just went with it. But you can always use quadratic equation. All it means is you're just going to have to do more algebra here. So you would have to take this quantity, you'd have to multiply it on the left-hand side, you'd have to distribute, and then you'd have to bring the x squared over. So remember, when you use quadratic equation, it has to be 0 equals ax squared plus bx plus c. That is the only thing, but you can always use quadratic equation if you prefer. So I hope that answers your question. That's Aga K, but that's a really good question. And it's good to point it, because I've forgotten about doing the 5% rule, that you can check and see if you can drop x before you do the calculation, which is what I like to do. But then you can check it afterwards and make sure that, okay, so I did this approximation. Is this all right? And if it's less than 5%, you're all good. Okay. All right, great. All right, so let's go on to our next one. We will be going back to more equilibrium, I promise. Okay, so now we're on to codeine. All right, so there's codeine, and it is a really big molecule. Okay, so codeine is a weak base. The pKb of codeine is 6.05. A 10 milliliter solution of codeine contains 5 milligrams of codeine. What is the pH of this solution? So you don't, I know, often think of like medications that you take as having a pH, but they absolutely do. And it's something that pharmaceutical companies also take into account when they are formulating drugs as well, although I know very little about that. So, all right, so we've got codeine, we've got a pKb, and again, we're calculating a pH. So this is very similar to the previous problem, because we're going to be dealing with equilibrium. But in this case, instead of just giving a concentration, we're given an amount and a volume, and we're also going to have to deal with this pKb. So this is similar, but again, we're adding in a few more twists just to make the problem, well, a little bit more difficult. But again, so you bring in more of these concepts and you synthesize them in these acid and base problems. So I am not going to start with my ice table right away, because what I really want to do is I want to get concentration first and use that concentration in my ice table. So I am actually going to start with concentration here. So I have a 10 milliliter solution and I've got 5 milligrams of codeine. So again, remembering that molarity equals moles of solute over liters of solution. That's a little bit messy. Hopefully you can read that. I need to take this milligrams to moles first. And of course, this 10 milliliters to liters is not a problem at all. So let's first take my milligrams of codeine and convert this into moles. Okay, so I'm just going to do some conversions here. Again, as always, make sure that you are writing down your units so that you don't accidentally flip-flop something. All right, making sure this is milligrams. So actually the first conversion I'm going to do is I'm going to convert from milligrams to grams. Now, I guess you could have done that before you started. But anyway, okay. And then now that I am in, this is actually still grams of codeine. That's kind of squashed there. So now I want to use the molar mass to convert to moles. And so I'm going to end up with moles of codeine up here. And my molar mass, I did look this up. This is 299.370. That is grams of codeine. So again, just making sure my milligrams of codeine have canceled, my grams of codeine have canceled. I am left with moles of codeine, which is exactly what I want because I'm going to plug it right in there. It's always nice when you can to go back and double check before you start throwing things into your calculator. Then I feel like once it's in your calculator, you've kind of committed to it, or at least I have. Okay, 10 to the negative fifth, and now this is moles of codeine. All right, so now let's get concentration. Okay, so my concentration of codeine, just to make this easier, because this is a big molecule, I am actually just going to call this B for base. All right, that's just going to make my life a lot easier. All right, so my concentration of my base of my codeine is going to be my moles here, 1.67 times 10 to the negative fifth moles. And this again is going to be over my liters of solution. So I have 10 milliliters, again, just dividing by 1,000 here. Liters. And so this gives me a concentration of 1.67 times 10 to the negative third. And that is molarity. All right, this just makes it easier when I plug it into my ice table. Although, alternatively, you could have stopped with moles of codeine and you could have also used that in your ice table. This is another situation where just do the way that makes the most sense to you. Now, for my ice table, because I don't want to keep writing out the molecular formula for codeine, I am going to use this B for base. So this is just a very generic way to write this equilibrium problem. So I have my weak base, my codeine, it is in water. Remember, bases are going to accept a proton, and then I am left with hydroxide. So it has taken a proton from the water, which means hydroxide is left over. I made an extra mark there. Okay, so now I'm ready to actually plug numbers into my ice table. So I'm going to take my concentration of my codeine, my base, 1.67 times 10 to the negative third. Again, just like when we did our acids, you can keep the water column just totally blank. That's not a problem. Of course, initially I don't have any product, which makes it really easy. You know which way the equilibrium is going to go. You don't have to bother with calculating Q and figuring any of that out. And now I'm just adding my columns here. 10 to the negative 3, that is going to be minus x. This is x. This is x. And now I'm going to have my Kb for base is going to equal my protonated base times my hydroxide. Again, I'm just pulling from my balanced chemical equation over my original concentration of base. And so I need to do a little side calculation because I want Kb here, but they gave me pKb. So let's just do a little side calculation. pKb, that P is just like in pH. It just means you take the negative log. So my pKb is just my negative log of my Kb. So it's really easy to switch back and forth between Kb and pKb. This is also handy to know if you are looking at a table of either pKa's or pKb's. You can always get back to either Ka or Kb. So my pKb for codeine is 6.05. This, of course, equals negative log of my Kb. So I can solve for Kb. And when I do that, I get a Kb of 8.91 times 10 to the negative 7. All right. Now I'm ready to go back to my equilibrium here and plug things in. So I have a value for my Kb, 8.91 times 10 to the negative 7th. And I'm just going to put in my equilibrium concentrations right here. Again, this is going to be x times x, or x squared. And in my denominator, I have this quantity here, 1.67 times 10 to the negative third minus x. And of course, yes, I can use quadratic to solve this, but that's a lot of algebra and I would rather not. So I'm going to check my 500 rule and see if I can drop this minus x. I might have to go to another page here. This is getting a little bit crowded. Okay, so my 500 rule. This is where I kind of wish I had just a regular sheet of paper that I could keep scrolling down on. Okay, so what I'm going to take is my original concentration of base over my Kb, and this should be greater than 500 if I want to drop this term. So my initial concentration is 1.67 times 10 to the negative third, and my Kb I just calculated over here, times 10 to the negative seventh, and I did that calculation, and that gives me 1,874, which is greater than 500. So yes, I can drop this term right here, which makes my algebra just infinitely easier. Okay, so coming back up here, I'm just going to rewrite this, and I'm going to drop that minus x term. And just make sure when you drop this term that you're just dropping the minus x. I have done these problems before where I accidentally dropped the whole denominator and I got the problem wrong, because you do need to keep this 1.67 times 10 to the negative third in the denominator. That was kind of a stupid mistake that I made one time. Okay, so this is a lot easier to solve for x because I'm just going to bring the denominator over to the left and take the square root. And I did that, and I get a value of x of 3.86 times 10 to the negative fifth. Now again, you've solved for x, and that always feels like, okay, I've solved for x, and that should be the end of the problem, because that's what we do in all of our math classes, right? But remember what x is in the context of your chemistry problem. So x is our concentration of our protonated base and our hydroxide, and we can also calculate our concentration of codeine. The problem has asked us for pH. Okay, so what we really want to connect this to is hydronium, but I don't have hydronium, right? But I have a concentration of hydroxide. So what I'm going to do instead is I'm going to first calculate what my pOH is. So my pOH is just simply negative log of my hydroxide concentration, which guess what is my value of x. Huzzah. All right, so this is just going to be negative log of 3.86 times 10 to the negative fifth. That is molarity. And that gives me a pOH of 4.41. All right, so again, the temptation here is to say, I have done this problem, I finished, but you have calculated pOH and they want pH. Also, if you're thinking about kind of your nature of acids and bases, then this is a base. It should have a pH of greater than 7, right? Well, if you had forgotten that this was pOH and you had calculated this and thought this was a pH, hopefully some red flag should be waving at this point, because you have something that's less than 7 that wouldn't be a base. But this is pOH, which means that to calculate my pH, I'm just going to take 14 minus 4.41, and that gives me pH, and that gives me a pH of 9.59. That makes a lot more sense for a base, right? To have a pH that is greater than 7. So that's another place where, again, I see students stop and they've actually calculated pOH, but they think they've calculated pH. So just make sure that the answers that you're getting make sense in the context of the problem. Okay, so that's great. That is this problem, and I see that it's actually 7:55. So there is no way that I'm going to get to the next couple of problems. But what I'll do here just in the last 5 minutes is I'll show you the problems, and I'll kind of talk through how I would approach these problems at the very least. And then you guys let me know in either the comments on this YouTube live stream, or you can, message me on Facebook or email if you want to see me actually work these problems, or next week I can just jump straight into reacting acids and bases together. Okay, but let's just look at these couple problems here. So this one says 20 milliliters of glacial acetic acid, and they give us the formula, and the Ka is diluted to 250 milliliters. What is the pH of the diluted solution? And they give us the density of glacial acetic acid. The thing that you have to, and this problem didn't specifically say this, is glacial acetic acid, you can assume that that is pure acetic acid. So this is really a density problem to then get to concentration. So what you would need to do is you would need to take this 20 milliliters, use the density to convert it to grams, then use the molar mass to convert it to moles. You know the volume, you can get the concentration. So once you have your concentration of acetic acid, then of course you can get to the pH, because this is a weak acid. So again, you would have to set up your ice table because it's a weak acid. But in terms of this problem, you can actually drop that more complicated minus X term in your ice table. So this is a situation where it's not straight up. You don't have moles. You don't have concentration. You have to get to concentration. So again, it's pulling you have a volume, you have a density. You've got to go to grams, then you've got to go to moles, then you've got to go to concentration. One of the tricky things about this problem is you have two volumes, so you need to make sure you keep straight which volume is which. This is your volume that you're going to use the density of. This was the original amount of glacial acetic acid. This is your volume of your solution that you're going to use when you calculate concentration. All right, so that was that problem, and I did have one other problem. A 1 times 10 to the negative second molar solution of cyanic acid has a pH of 2.77 at 25 degrees Celsius. And then the question is, what is the pKa of cyanic acid? So this again is kind of working backwards. Usually we are given a Ka or a pKa, and we use that to calculate different concentrations. But in this case, we want to actually calculate our pKa. So for this problem, you would take your cyanic acid, you would set up an ice table. This is a weak acid, otherwise they would not be asking for a pKa in this case. Once you set up your ice table, you'll end up with a situation where you have your Ka equals to like your X squared over, your concentration minus X. And you're going to look at that and you're going to say, wait, I have two variables. I don't know my Ka, and I also don't know my X, and I cannot resolve this because, of course, if you have two variables, you need two equations. But you actually know what X is because you are given the pH. So remember that your pH is connected to your concentration of hydronium. Once you know your concentration of hydronium, that is your value for X. So in this case, instead of solving for X, you're going to plug X in to your equation for Ka and use that to calculate Ka. And that is how you would handle this problem. Again, a really interesting problem where you have to think about it in a different way, even though you're using the same tools to do the problem. So thanks so much for joining us for the live stream. Again, next week, if you guys really want to see these two problems actually worked out, I am happy to do so because they are ready to go. But I will also be doing reactions of acids and bases together. So you can think of that as neutralizations. And again, I'll try to do the same kind of thing where it will do kind of just a really simple straight up neutralization problem. And then I'll try to add some twists in so you can bring, again, different concepts in and see how different problems work. Anyway, thank you so much for joining me. And please feel free to leave a comment. Let me know what other topics you want to know. Again, it's easy to contact me you can do through YouTube, you can do through Facebook, you can do through email. My email is in the description below. And I hope that you guys have a wonderful rest of your day. Thanks so much. Bye.